Okay, and then I think we worked through letter C, which was a good practice in your properties of logarithms. So I'm not going to redo that one, but that worked through your properties of logarithms. If there's any of those you're unsure about, please, please, please come by and see me. Okay? All right. So now let's do something that kind of more incorporates the natural log. I hope this will fit on going across. If not, we'll wrap it along. But this is going to be kind of a lengthy one. But again, the point is just that we're incorporating this new derivative rule into all of our other rules. So what do I have to do for this first term? Yeah, Angel says the product rule. You agree? Yeah, we got the product rule here. So how do we do that? We take the first factor, which is x cubed times what? What do you say, Justin?
Derivative of natural log, so just one natural log.
Yeah, so the derivative of the natural log of x, which is 1 over x. You could write 1 over log base e times x, but log base e is what? What's log base e? Yeah, it's 1. Okay, so that was my first derivative of the second plus the second times the derivative of the first. Okay, so far so good? Okay. Plus, now we're going to take the derivative of the tangent. Oh, sorry, what do we have here? We've got another product rule, right? So it's the first times 1 over x plus the second. What was the derivative of the tangent? Secant squared. Okay. So Freddie, what's going on with this next term?
It's the chain rule. It's natural log of x within secant.
Yeah. Okay, so what's the outside piece? The secant of x, right? So first we're just going to take the derivative of the secant of the expression, leaving that inside expression alone. Okay. What's the derivative of the secant of an expression?
Secant x tan x.
It's plus the secant x. So secant of what's inside there times the tangent of what's inside there. Oops. Times the tangent of what? Natural log of x. Can you guys see that okay? I know I'm writing small. I'm trying to fit it in. I'm not going to make it across the page anyway, so it's not, I don't know if it's worth it. Okay. Now we've got the chain rule, right? And we multiply by the derivative of what was inside. What was inside my secant expression? Natural log of x. What is the derivative of the natural log? 1 over x. Okay. Okay. So let's see here. Stephen, you want to help me through this next one?
Would it be 1 over cosine x times negative sin x?
Yeah, so talk me through this. It's a what type of rule problem here? What rule do we have to use? And I think you used it correctly.
We'd use the natural log rule.
So the derivative of the natural log, okay?
Multiplied by the chain rule.
Yes, exactly. So the big picture is this is a chain rule problem, right? So we're going to take the derivative of the outside piece. Who's the outside piece in this case? Natural log. Do you see in the last case the natural log was the inside piece? Okay. All right, so Stephen said, okay, well the derivative of the natural log of an expression is 1 over that expression, right? Times what? Maggie, what are we going to multiply this by?
Negative sine x?
Why negative sine x?
Because it's the derivative of cosine x, which is the inside.
So the inside function here was cosine of x, right? And so I'm getting to do the chain rule, so I'm going to multiply it by negative sine of x. Do I put it down here?
No, off to the side.
Exactly. We multiply the entire derivative of the outside by the derivative of the inside. Questions on that? Okay. Plus, let's see. JP, you want to help me with this next one?
It'd be similar to the last one.
Okay, I agree.
So the 1 over 3x
Okay, so it's a chain rule problem, right? Everyone see that? It's a chain rule. It's not a big chain. It's not a difficult chain rule problem in that inside expression. It's not x, but it's similar to x, so it's not going to be significantly different. But it's still technically a chain rule problem, right? Okay. So the derivative of the natural log of an expression is 1 over that expression. In this case, the expression is 3x. And then what do I do? Times the derivative of the expression, right? JP, what's the expression? So the expression is 3x, and so its derivative is 3. By the way, what happens to this in this case? Interestingly enough, they cancel. So the derivative of the natural log of 3x is the same as the derivative of the natural log of x. That's kind of interesting. Okay, great. All right. So let's work this last one together. Okay, what's the big picture here? Quotient rule, right? Somewhere inside doing the quotient rule, we're going to have to do some whats? We're going to have to do a chain rule because of this complicated expression inside the natural log there. What else are we going to have to do? Product rule. Where are we going to have to do the product rule? In the denominator. So do I start off doing the product rule?
No.
No, not until I get to the part where I'm saying the derivative of what? Not until you say the derivative of the bottom do you start doing the product rule, right? So I'd like everyone to give this a shot. So we do it together. We give it a shot first. And then we'll try it as a group. Any volunteers? Michael, give me a hand with this. What are we going to start with?
So you would first start off with e to the x power times L and x.
Okay, why that?
Because that's the low.
The low function, right? The bottom function. Good. Then what are we going to do with that?
And you're going to multiply it by the derivative of the top function.
Okay. So I want to talk about the top function real quick. The big picture on top is that I've got how many terms? I've got 2 terms separated by what operation here? Subtraction. Okay. Folks, if you're just looking at all expressions the same way, I encourage you to start separating it. Put the vocabulary to it. We have 2 terms separated by subtraction here. Okay. So when we go to take the derivative of these 2 terms, we're going to do it term-wise. So let's go ahead and take the derivative now of this first term right here. Okay? Help me out.
The x squared minus 3 times 2x.
So that was the derivative of the natural log of an expression is 1 over that expression. Good. But that expression was more complicated than just an x, so we multiplied by the derivative of that expression. Great. So that was the derivative of this first term, okay, minus the derivative of the second term, which is 2. Great, thank you, Michael. So we had the bottom times the derivative of the top minus the what? Goes next. Minus the top function, which would be the natural log of x squared minus 3 minus 2x, all times what?
The derivative
The derivative of the bottom. Okay. Yeah, we're going to have to use the product rule on it. Riley, you want to help me out with this one? Okay, so we're doing a product rule, and that's the first term. Good. Great. What's the derivative of the natural log? Careful. So if I give you f of x equals the natural log of x, its derivative is 1 over x, right? Yeah, that's right. So we've got, but I think we got it now. So we got the first. Good. Plus the second. Good. Times. Good. And what's the derivative of the first? Very good. E to the x. Well done. Awesome. Okay, sorry I had to run a little long with that expression. I tried to make it small, but I guess not small enough. All all over what? All over what, Marissa?
The bottom square.
The bottom function squared. So the best way to write it is probably just like this. And since I'm not asking you to simplify it, let's walk away from that. Okay? That was extremely messy, folks. That's all your problems put together in one. Okay? But it's kind of nice to look at each one of them and look at the similarities and the differences. I've tried to pick these in such a way that, you know, here the natural log was on the outside, here the natural log was on the inside for the chain rule. Okay? Here we incorporated with some product rules, etc. Okay? So folks, I think these examples, the ones where I write out, it's a big long expression. I know they look complicated. One, I'm not going to ask you one that hard on an exam. But I think that they're good examples to rework through a couple of times to make sure you can get all the components. Because I've tried to, and there's many ways you can combine derivatives, but I've tried to incorporate some of the most common ones and also some of the ones that give students the hardest time. Okay? All right. Let's talk about number 8 here. We want to take the derivative of the natural log of the absolute value of x. So we were actually just talking about the absolute value function. Of course, this absolute value function shows up inside the natural log. But I think we should still break it up. Okay? Before we do so, let's just identify the domain of f. What operations am I doing that could get me into trouble?
If it's 0 or negative.
So I'm taking a natural log, right? And we can only take the natural log of positive numbers, right? Okay, so normally if I just said, here's g of x equals the natural log of x, the domain of g goes from, careful, not including 0, to infinity. Careful there, that's a soft bracket. Let me make sure that looks like a soft bracket. Okay? But what? What's going on here? What do you say, Derek? What's going to be the domain of this function here? Dalton, what do you... Sorry. Derek, answer the question.
It's
sorry,
absolute value, so it'll always be positive.
So will it always be positive?
You take the absolute value of x, it will be positive.
Is that true for all numbers? Is it true for all numbers? Like certainly, if I agree, if I take the absolute value of -2, I get a positive number. I get a positive number 2. Well.
It's all x that are not 0.
Ah, so careful with that, right? Everyone. So not a bad response, right? All the negative numbers I can now go ahead and plug into this function. I can plug in where normally I can't plug in a negative number into the natural log. Okay, I can plug a -2 into the natural log of the absolute value of x. That's fine. But there is one number still excluded. Who is it? 0. Because what's the absolute value of 0? It is 0, and 0 is not in the domain of the natural log. Okay, so the domain of this function f here is -infinity to 0, union with 0 to infinity. Okay? So the domain has 2 parts. Let's go ahead and find the derivative in each part. Okay? So if x is in the first part, sorry, I said first, but I mean the rightmost part. If x is greater than 0, then how can we rewrite f of x? It would just be the natural log of x, right? Somebody said I should start putting parentheses around this when I apply the absolute value rule, so you can see I just applied the absolute value rule. Okay. All right. So now, what is the derivative of f? It's 1 over x. Good. All right. What if x is less than 0? Then, when I go to take the natural log of the absolute value of x, what can I replace that with? The natural log of -x. Now careful, am I inferring that we're going to take the natural log of a negative number? No, because what's the sign on x? Negative, and then what do? We stick another negative in front of it. So what's the sign on the argument inside the logarithm? Well, yeah, that'll be the derivative. Good, good. The sign on the argument, the sign of the stuff inside the logarithm will be positive, though, right? Okay. So now we can go ahead and take the derivative of this, okay, which is 1 over what? What is it? What's the derivative of the natural log of an expression? 1 over that expression. So I'm going to put 1 over what? Negative x.
Times negative 1.
But now, because there's a chain rule here, I have to multiply by the derivative of what was inside the logarithm. And the derivative of that is a negative 1, right? So we also get 1 over x. So what is the derivative of the natural log of the absolute value of x? It is just 1 over x, and this holds if x doesn't equal 0, which is great because the function itself isn't defined at 0. So actually this is a pretty well-behaved derivative. We didn't lose any values when we took the derivative of it. The derivative is defined at the same place that the function was defined. Okay. Keep that derivative in the back of your mind because this is a very important one, and we'll need that come chapter 5. Okay? This one's a fun one. I'd like you to try it. Yeah.
Can we just continue this problem from the one above?
Yeah.
As like the second half of the chain rule?
Yeah. Yeah, so I see an absolute value here, but we just learned how to take the derivative of the natural log of an absolute value of an expression. So you don't have to reinvent the wheel. You don't have to go back to the definition here. So yeah, so you can't, there's some thinking that goes on, but you don't have to write out 2 different cases like I did in the last instance. What do you think? Is this going to have a messy derivative? This is kind of actually an elegant one. The derivative of the natural log of the absolute value of an expression is 1 over that expression, right? No absolute value, right? We saw what happened to the absolute value mark in the last problem. Okay? But then because that expression was more complicated than just an x, I now need to, by the chain rule, multiply by the derivative of what was inside the natural log of the absolute value. What is the derivative of secant x? That's a kind of a nice derivative. You'd think it'd be kind of messy, but it comes out well. What's that?
Because the secant's cross.
Exactly, exactly. Great. All right. Yes?
Is that the derivative for secant x, whether the absolute value is applied in that function or not?
It is, but you would then have to specify where, because tangent appears to be defined everywhere except for odd multiples of pi over 2. But this expression is, if their absolute value weren't there, would be defined for, it does have interesting stuff happening at odd multiples of pi over 2, but also the secant curve is sometimes negative. And so you'd have to then, you just have to be much more careful talking about where the derivative exists.
You'd have to extend it.
Mhm.
otherwise, right?
Mhm. And in fact, here I guess we should still say that this holds for x. But it's not, well, no, because it's nothing new. We already knew x wasn't defined at the odd multiples of pi over 2 here, so we didn't lose any new information when we took the derivative. I think if you take the absolute value away, though, you still don't lose any more information, but it's just, yeah. but do know that they are two different functions if I take away the absolute value, because they have different domains. All right. Did you guys watch your video?
Yes.
Yeah? The Scottish mathematician John Napier invented an early form of logarithms that we now call Napierian logarithms in order to make whose lives easier? Yeah, to make sailors' lives easier. What's the issue? You could teach a sailor to add, you can't teach him to multiply. Okay? Oh, I don't know whether the video went, I can't remember, I haven't watched it this semester. Basically logarithms take advantage of the fact that for exponentials, a multiplication problem can be rewritten as an addition problem. Then if you just have some information you can look up in tables, you can do hard multiplication problems simply by looking stuff up in tables and by doing some addition. Okay? So if we had more time, we'd actually look at that. That's an old-fashioned way of how people used to do large multiplication problems. And in fact, they actually built a whole instrument based on using logarithms and their properties of addition to do multiplication, and it was called the slide rule that made hard multiplication problems easy to do, and a lot of other things. Anyway, it's an interesting video. If you haven't watched it yet, you should. Okay, a little bit of math history for you. But it is kind of interesting. Logarithms are one of the first things I can think of that we say, we invented this for a purpose. And then the mathematical theory came about later on, and we ended up really appreciating logarithms and incorporating them into the rest of mathematics. But it was originally just supposed to be a practical technique. Okay. All right. Number 11. Product, quotient, and chain rule can sometimes lead to some tedious bookkeeping. True?
Yes.
Whenever we can, it's nice to avoid them. Okay? Sometimes we can use the properties of logarithms to break down an extremely complicated expression into a bunch of terms involving logarithms. Okay? So we're going to call this technique the technique of logarithmic differentiation. I am actually only going to work one example of it because all the other examples would go the exact same way. But by working only one example, I'm not saying it's unimportant. You are guaranteed to have a logarithmic differentiation question on your next exam. Okay? So this is how it works. Okay? I don't think that you would like to take the derivative of this expression. I'm not going to recopy it for sake of room. I don't think that you'd like to take the derivative of this expression. Why not? Because the big picture is it's a quotient rule, but to do the derivative at the top, you'd have to do a product rule, and that product rule has some chain rule elements to it. Okay, and then when you do the derivative at the bottom, you've got a chain rule. Okay, so it's a pretty messy expression. Okay, if you think that you could do it, because I don't think it's an impossible problem, I think it's far from being impossible. Okay. That's great, but could you imagine one even larger that just gets more? I mean, some of you have done some triple product rules, right? Some of your homework questions. So you've seen some triple product rules. They do get, you could make this thing get messier and messier as you go. Okay? This technique will help as long as all you have are multiplications and divisions for your major operations here. Okay? So what am I going to do? I'm going to start off by taking the natural log of both sides. Turns out that even though logarithms made sailors' lives easier, they make our lives easier too. So, in the numerator, I'm going to do this, I hate to say it, folks, I'm going to do it in one step, but let's talk about it. In the numerator, the big picture is I have two terms that I'm doing what to? I'm multiplying them. I should have called them factors. I have two factors that I'm multiplying together, right? Okay. So how can we break up multiplication inside of a logarithm?
Addition.
Right? We can let it be addition outside the logarithm. Okay? So I could write this, and don't write this just yet. I could write the first term as x to the 3/4 power. Don't write it just yet. Plus the natural log of x squared plus 1 all to the 1/2 power. True? Does everyone see what I just did? I haven't written the bottom part yet. I haven't gotten there yet. Okay? But in fact, I could also do what with these powers?
Moving forward.
I could move them out as factors. And what do we know about factors, constant factors, when we take derivatives? They just come along for the ride. So it's a lot easier if we can divorce the exponentials from their powers, which we can do this way. Okay. Minus 5 times the natural log of 3x plus 2. Okay? Everyone see what I did there? If you didn't see this, then I need to explain it.
Isn't it plus 1/2?
This should be a plus 1/2. Thank you. Good call. Good call. So then I was dividing all these two factors by this factor, so I brought that out as a subtraction of a logarithm, and then I pulled the 5th power out. Now, can I pull this second power out? No, because it's not distributed to the entire argument inside of the logarithm. All right. I have just taken this complicated problem. I took the natural log of both sides, and now I have the sum of 3 much more smaller terms, right? Now, this is the part where people get into trouble, because they don't like to write this step. I know the reality is some of you didn't write that down. Okay. But do I still have y on the left-hand side? Is it just a y?
No.
It's a natural log of y. So now it's no longer, y is no longer an explicit function of x. This is now an implicit function of x, so I'm going to have to use what technique? The implicit differentiation technique that we talked about last time. Okay? So now I'm going to take the derivative of both sides. So let me just say differentiating, so I don't have to recopy it and put the d dx on each side. Differentiating, we get, what is the derivative of the natural log of y? 1 over y, and in the same breath, as Will said, times y prime. Don't forget that chain rule that comes from comes from implicit differentiation. Okay? But on the right-hand side, look how easy this is. This is 3 over 4x. Plus 1 over 2 times x squared plus 1 times 2x. Minus 5 over 3x plus 2 times 3. And that was pretty easy to take the derivative of. Okay. Now, we're not done with this problem. And again, some people like to shy away from complicated notation because it looks complicated. I say embrace it. Practice it. Okay? Is this y prime right here on the right-hand side?
No.
No. Because this expression on the left-hand side isn't y prime. If I want to find y prime, what do I have to do?
Multiply.
Yeah, I'm hearing folks say it. I've got to multiply this y over to the other side. Okay? So let me do so, and it looks like I need some more room. So we'll take it over to another page here. See if I can do this. Okay. Okay. So multiplying this y over to the other side, we get y prime is equal to y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. I've got one more step before parking my answer. Okay? The original problem wasn't an implicit function of y, it was explicit. So what can I do? What's that? Plug in what y was, right? What was y? Well, it's over on the other page. Let's see if we can remember. It was this large expression right here. I'm going to plug it in for y. Okay? So I might need a hand with that because I can't see it, but I think we had y prime then is equal to x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th times now all of this times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. What's that? Well, yeah, great. So what is this right here? That's y. I can't have y in my answer, so what? Go ahead, what did you say we did? We substituted what the original equation for y was, which was listed right here. Good. Okay. All right, folks, this is the only one that I'm going to do that is large and complicated, but you will have a large and complicated problem on your exam. Okay? And I will probably say use the technique of logarithmic differentiation. If I do that, you must use this technique. Okay? You might say, hey, it would have been easier to just do products chain rules on this. Well, I could just add in a few more products and a few more chain rules, and eventually it'd be so complicated that you'd be very thankful for this technique. Because notice that although it was a lot of writing, there was never any complicated computation that you had to do. We had some mini chain rules, and that was it. Okay? All right. Everyone look at number 14. Discuss it in your group. Yeah, where do you want to go back to?
Just like this.
That page right here? Yeah.
Cool, thank you.
So I'm going to call on one of you groups. Come up with a good answer. So let's do this group back here. Why can't, what's the issue with trying to take the derivative of this function? What's that?
So I thought the question was, why can't we use product rule in this
Uh-huh.
situation? So that's why my explanation would be incorrect.
Okay. Yeah, so you can't use a product rule here. Okay.
Correct.
Remind me what the power rule is for. I'm asking why can't we use the power rule on this problem? Yeah, but remind me what the power rule says. It says if you have x to the n, then its derivative is what? nx to the n minus 1. What's the issue here? Why can't I use that rule?
There's no n.
Yeah, what does n stand for? It stands for some fixed number, right? Like 2 or pi or 27, but it can't be a variable in its own right, correct? Why can't I use the exponential rule? What was the exponential rule? It says if you have a to the x, that its derivative is what?
1 over 8, or natural log of 8 is
Yeah. Why can't I use that rule?
yeah, no way.
Because a stands for the fixed base of the exponential equation. Everyone see what the issue is here? So we want to summarize it?
You need a fixed number to use the rules.
Yeah, both of them. So to use the power rule, you need a fixed power. To use the exponential rule, you need a fixed base. And what do I have in this case? Yeah, I've got a variable for both the base and the exponent. By the way, if you've never played with this function, that's too bad because it's a lot of fun. Okay, let's look at, if I say f of x is equal to x to the x, what's f of 1? It's 1 to the first power, which is 1. Okay. What is f of 2? It's 2 to the second power, which is 4. What's f of 3? 3 to the third power, which is 27. What's f of 4? 4 to the fourth power?
128.
All right, let's see, 4. Yeah, it's 256. This thing gets big fast. Okay? I can't even do this one. 5 to the fifth power? Ooh, 6,000, 3,625? What's that? 3,125. It gets big fast. Faster than an exponential function even. Okay? All right. So, I still want to take its derivative. I still want to be able to describe how quickly it's changing. Okay? Well, what could we do? Marissa?
I actually have a question.
Yeah.
Couldn't you get into trouble with this one where you start to get to where you can't find the derivative of it? Because eventually it would be almost vertical.
Almost vertical, but not vertical. Right? It keeps getting steeper and steeper, but it does not have, for instance, it does not have a vertical asymptote. Right? So it does not be, and so it never becomes perfectly vertical. It's still, as you go to the right and go up, you'll eventually intersect the graph. You'll just have to go a long, long ways up. Yeah, that's a great question. So this does have, these tangent lines, you can envision this graph is very, very steep, so the tangent lines are getting close to vertical, but they don't get exactly vertical. There's always just a little bit of positive right direction as you move to the right. Yeah. Yeah. But we're going to see that this has a very, very large derivative when we go to take its derivative. What technique are we going to use here, folks? We're going to use the technique of logarithmic. Everyone say this. Come on, folks. This is what? Logarithmic differentiation. How do you use logarithmic differentiation?
Take the natural log of both sides.
You start off by taking the natural log of both sides. Why would we want to take the natural log of both sides? Somebody give me a good explanation. Not what does it do, but why would we do that?
Well, if you're going to do it to one side, you have to do it to the other.
Okay, so first of all, if we want to take the natural log of one side, we have to do it to both sides.
You want to make
What?
this implicit.
Okay, implicit. We're eventually going to have to use implicit differentiation. Sawyer, why do you think we're taking the natural log of both sides?
I think because there's a lot of ways to simplify it. Like you can use log, or you can use things like that. You can use also the properties of ln or logs.
Everyone hear that? Yeah, I agree completely with that, right? So we've got the properties of logarithms that allow us to break up complicated expressions. I don't know how to take the derivative of x to the x. But if I could somehow separate this power from this base, then I might be able to be in business. Okay? Is that what you're going to say, Will?
Yeah, I was just going to say, would it be valid to say that if you approach it from the opposite direction of, I need to turn this expression of two variables related to each other by an exponent into some expression that's not an exponent. The only reasonable way to do that is with the properties of logarithms.
Yeah, so I think one of the most beneficial tools of the logarithm is it allows you to separate a base from an exponent. That can be highly advantageous, and that's precisely what we need to do in this case. So what can I do for my next line? Kaylina, what do you say? What can I do over here? That's right, you can talk. Talk to a friend. What do you think we should do here?
Smooth.
What do you think, Kaylina? What should we do?
Well, I guess.
Well, so notice we're not taking the derivative yet, right? I haven't taken the derivative either side yet. All I'm trying to do is simplify this problem. So what could I do to simplify this, the expression specifically over here? I want to simplify this expression. Yeah, so this is complicated because I've got what? I've got x raised to the power of x. What would I like to do? I'd like to somehow get that power away from this x right here. What could I do to do that? Yeah, go ahead.
Can you bring it forward?
Exactly. Everyone hear that? We can bring this x out of the power. Great. So this gives us x natural log of x. Does everyone see what just happened here? So now I can differentiate both sides. Okay. So on the right-hand side, Victoria, what do I get on the right-hand side when I differentiate both sides?
1 over 1 times the derivative of y, which is y prime.
Very good. And that was because of what?
Chain rule.
The chain rule. Okay? Alrighty. Will Garcia, what do I got to do on the right-hand side here? Okay. So what am I currently doing to both sides? Taking the derivative of both sides, right? Okay. And so what rule am I going to have to do to take the derivative of this right-hand side? What's going on between these two factors here? They're multiplied together, right? So I'm going to have to use the what rule? The product rule, right? Great. Okay. Aaron, help me out here. To do the product rule, what do I write?
So, is that if I do it my way? Like,
Yeah, sure. Yeah, I can follow.
So I did ln of x plus the derivative of x 1.
Okay.
Then plus x to the derivative of ln of x, which is 1 over x.
Great.
And the x cancel out, so just that just comes out.
Great. Yeah, so everyone does the product rule their own way. Okay. Which makes grading it difficult, but I adapt. Okay. So this gives us 1 over y prime is equal to just the natural log of x plus 1. Okay? Folks, so this is where the last problem is exactly identical to this one. I know we didn't have to use all that many properties of logarithms, but what is my next step? What do you say, Summer? What do you do next? Bingo. We're trying to figure out what the derivative is, so we're trying to now solve for y prime. So we get y prime equals y times the natural log of x. So Angel, what's my next step? We're going to do a substitution step here, right? Because this isn't my final answer. Why does this hold as a final answer? I've got this variable y here, right? Okay, so what can I replace y with? What do you say, Caleb?
That would be x to be x
So, this function, when I think, let's recap our polynomials. If I give you the function f of x equals x to the 5th, how fast is this thing growing? It's growing this fast. Okay? It's growing at a rate slower than it's actually outputting y values. Right? And if I give you this function, how fast is it growing? It's growing as fast as its output values. How fast is, so this goes to Marissa's question, how fast is this one growing? Well, this expression's bigger than 1 for all x values larger than e. So it is growing at a rate faster than, so this is above exponential. Okay. Cool beans. So if you remember, we gave a generalized power rule, and I said we got to hold off on the proof of it. Now we're ready for the proof of the generalized power rule. Okay, so here we go. If we look at y is equal to x to the n, we're going to pretend we don't have the power rule right now, and we're going to prove it. Okay? So we're going to pretend we don't have the power rule. Let's prove it. So what should we do? Let's use logarithmic differentiation. Okay? So, Mark, what am I going to do here?
We take the natural log of both sides.
I agree. Why would we take the natural log of both sides? We'd like to simplify things. So Kaylina, what's my step here? I'd like to simplify that right-hand side. What can I do? I agree. What should we do? Bring that in out, right? Okay. All right, now we're ready to take the derivative of both sides. We call this process implicit differentiation. So, taking the derivative of both sides, we get 1 over y times y prime is equal to n times 1 over x, right? So then that gives us that y prime equals n times 1 over x times y, but what was y? It was x to the n. So I'm taking x to the n and dividing it by x, so what power does that leave me with? Does everyone see this step? Marissa?
Actually, I have a question.
Yeah.
Why didn't you have to do the product rule for the n times
So here I am assuming that m is a fixed number. It's not a variable. So I am assuming that it's a fixed number here. If it weren't, it would be like the previous question. But actually, so what we're doing is we're going back and we've been using this power rule for a long, long time. We're going back and actually proving it now. So we are going to, this is sort of a step backwards, but we are going to pretend that that n is some fixed number, like 27 or pi or 3. Okay? What do I get when I multiply 1 over x times x? Talk in your groups. What do we get when we multiply 1 over x times x to the n?
Because you don't know what x is, so you just keep the variable and subtract it.
Right? When you divide by an x, that's the same thing as subtracting 1 from the exponent. Right? By your properties of exponents. And so what have we just proven? We've just proven the generalized power rule that we've been using for a long, long time. Okay? So if I tell you that g of x is equal to x to the pi, what is g prime of x? It is pi times x to the pi minus 1. Okay. Now, folks, correct my mistake. Correct my mistake. What did I just do that was horribly wrong? What's wrong with that?
It's more complicated than just.
I think you're on the right track.
Oh.
Justin, let's talk through it.
Oh, just a second, guys. It's more complicated than just x there, so you have to use the chain. Or no.
It's not quite the chain. You're right. It's more complicated. What rule did I just apply? The power rule. Does the power rule apply in this case?
No, because the power is.
The power rule, and this goes to Maurice's question, the power rule assumed that the variable was what? Sorry, that the power in the exponent was what? A fixed number. Right? So, this is not like the previous question. How are we going to do this one? We're going to use this logarithmic differentiation technique again. Okay, so here we go, one last time. This is our last time trying it. Okay? So, we'll say y is equal to x to the cosine of x. Okay? Will offered a good insight last time. Okay? He said, the natural log is a tool that helps you separate the power from the exponent. I don't know how to take the derivative of x to the cosine of x. What's the issue? Both the base and the exponent have variables in them. Far more complicated. So what am I going to do? Caleb?
I think you're going to first take the natural log of both sides.
Take the natural log of both sides.
Then you can simplify.
Kaylina, why are we doing that? Why did I just take the natural log of both sides? What can I do over here? Yeah, so let me ask you first, what's my next step? How about that? What am I going to do on this right-hand side here?
Well, like, my question is, like, are you bringing it forward to the,
I'd like to,
right?
right? Because if I said, hey, if somebody woke me up in the depths of the night and said, what is the derivative of x to the cosine of x? I'd say, I have no idea. Let me go back to sleep. That's not one that I have memorized. I have no idea what that derivative is. Do I know what the derivative of the cosine is? Sure. Do I know what the derivative of x is? Sure. But I don't know what the derivative of x to the cosine of x is. So I'd like to somehow separate them, right? So what do? We take the natural log of both sides, because in the next step, what am I able to do?
You bring it forward,
Bring what forward?
the cosine term.
Bingo. So we get to bring the cosine of x forward. So now I've got two separate factors that are being multiplied together. I no longer have a variable base to a variable exponent. Okay? All right. The derivative of this then is 1 over y equals the first times the derivative of the second plus the second times the derivative of the first. And on the right-hand side, I forgot my y prime. That's horrible. That's horrible. All right. So this gives me y prime is equal to, I'm going to multiply this y over, and just because I'm running out of room and we're running out of time, I'm going to replace it with what y is, times the cosine of x over x minus the sine of x times the natural log of x. Cleaning it up a little bit as we went. Sometimes, this is interesting, sometimes this is growing at a rate faster than x to the first power. No, that's not true. Sometimes this is growing as fast as x to the first power. Sometimes this is growing as slowly as x to the minus 1 power, and sometimes it's growing at some rate in between.
It's a step function though.
Well, not a step function, but yeah, it would be rising. Anyway, it's worth thinking about. All right. I want to go ahead and introduce you to this, folks, because this is, for those of you that go into math, engineering, physics, this is why you want to learn calculus. You want to learn calculus in order to solve what are called differential equations. A differential equation is a statement about how a function changes, and then you try to determine what function must satisfy that. Okay? So normally, I might say, find the number for x. And we'd say 3x plus 2 equals 7. What would you do? You would solve for x. And what type of object is x? It's a number. That's what you're looking for. X is a variable, but we're trying to find the number or numbers that x could take on to make this thing true. You're right that it's a variable. Okay? But specifically, the variable stands for a yet to be specified number. Okay? In later classes, you'll take something like y prime minus 3y equals 2x. And here we are looking for a function y that would satisfy this equation. Okay? I want a function y that would satisfy that equation. This is called a differential equation. Okay? We're not going to do them in this class. Okay? But there's a whole course in it, in differential equations, where you learn how to solve for functions that have certain properties. That's advantageous, right? Because in the real world, you don't necessarily know a lot about your function, but you might say, hey, the temperature on this day was 20, the temperature on the next day was 25. I know that over the course of a day, it changed by 5. You made a statement in the real world about the change of the function. That's a statement about its derivative. You want to then find a function that satisfies that property. Yeah, Will?
Also, just to be clear, this question is telling us to arrive at an answer where the derivative with respect to some variable is some linear multiplier of that, or multiple of that variable?
That's true.
Okay.
Yeah, yeah. And in fact, so then, boy, I don't know if I can do it. 3 halves. Yeah, I can't do it. I can't solve. If I give you this one, I can solve this one real quick. So if I gave you this, a solution to this would be y equals a constant plus another constant times e to the 3x power, e to the 3x. Okay? This function solves this equation here, and you can check to see that that's true. When you take its derivative and then subtract 3 times the original amount, you get 0. I don't want to spend a lot of time on that, folks. I just want to introduce it to you. Okay? Because in reality, I mean, calculus is the language that you use going forward in the sciences. Okay? But in reality, what a lot of scientists are solving is complicated differential equations, okay? Which requires an understanding of what a derivative is. Okay, so real quick, look at this phrase. The growth rate is proportional to the population. I want a function whose derivative is proportional to the amount that I have. This is a differential equation, and this is the most basic differential equation that you solve in a differential equations class. And it's one that's already been solved for you in a lot of the applications you've already seen. But the hallmark trait of this particular differential equation is that the rate of change is proportional to the amount you have. Think about that for just a second. If I have just one bacteria cell sitting in a petri dish, it's not going to grow very quickly. But if I have hundreds of bacteria sitting in a petri dish, it's going to grow proportional to that hundreds of bacteria. The growth rate is proportional to the population. Well, it turns out that this is a solution to that differential equation. Y of t equals c naught e to the k, and that should be times t, folks. There's a typo there. Okay. Let's just check that. What's the derivative of this function? It'd be c naught e to the k t times k, right? Everyone see how I just took the derivative of that? C naught stands for a constant, right? K stands for a constant. What's the only variable in this expression? The t, okay? And the derivative then of an exponential function is just e to that expression, but then by the chain rule I had to multiply by the derivative of k times t. What's the derivative of k times t? It's k. All right, so you guys have seen these before. You have seen this function be a solution to equations before. It turns out that if k is positive, then the function exhibits exponential growth. Okay? If the k value is negative, then the function exhibits exponential what? Do you remember? I heard it. So we say it out loud? Okay. Exponential decay. Okay? Okay, these are your growth and decay problems. Okay? By the way, a personal pet peeve. Don't say something's growing exponentially if it doesn't fit this model. People use the phrase it's growing exponentially just to mean it's growing fast. That's not true. That's not what exponential growth means. Okay? All right. So let's just do this one problem here, and then we'll call it good. Okay? For this section. The half-life of strontium-90 is 28 days. I don't know what strontium-90 is. I know it's a radioactive isotope, which means it starts emitting some of its particles, and so it eventually starts to decay. It's radioactive. That's all I know. Okay, I don't know chemistry. Most of you probably know chemistry far better than I do. Okay? But we're given its half-life. That means that if we started out with 100 grams of it, after 28 days we'd have 50 grams. After another 28 days we'd be down to 25 grams. Okay? A sample has a mass of 50 milligrams. Let's build a function that tells us the amount of mass A remaining after t days. Okay? Well, I didn't say this, and I should have added this, that it decays proportional to the amount left. That means that the more you start with, the faster it decays. Once it's gotten down to you just have a little bit left, it decays slower. Okay? Well, that is precisely the description on the previous page of a differential equation. So we know that a prime of t has to equal k times a. That's a differential equation. Why is it called a differential equation? It's got a derivative in it. Okay? We're trying to solve for that a value. Okay. Well, I told you, we said on the previous page that the solution to this is a of t equals c naught e to the k t. That's a solution to this differential equation. The difference between this and a college algebra class is, in a college algebra class they just say, use this function to model this scenario. We're starting from this first principle, which actually describes the behavior of the thing that we're studying. We then build an equation from that. We then solve the equation that becomes our formula. Okay, so that's how this is different from your college algebra experience. Okay? Okay. So how much should we start with? So I know that when I plug in 0, it better spit out what? 50. Well, that tells us that 50 is equal to c naught e to the k, I still don't know what k is, but times 0. What's k times 0?
0.
It's 0. What's e to the 0? It's 1. So we get that 50 is equal to c naught. Okay? Which is why I've been using that subscript with a 0 on it, because it stands for the original amount. Okay? So we're partway through building our model, right? We've got that a of t equals 50 times e to the kt, right? Is this a workable function? Can I actually use this function? No, why not? I don't know what the constant k is, right? So I need one other piece of information. Well, I know that after 28 days, how much should be left?
25 milligrams.
After 28 days, a half-life has occurred, so I should have half of what I started, right? As Freddie said, we should have how much left after 28 days? 25 left, right? So let's plug this ordered pair into the function here. We know that 25 is equal to 50 e to the k times 28, or 1/2 is equal to e to the 28k, and I can solve this expression now for k. What should I do to solve for k?
Natural log.
What should I do? We're trying to get k, we're trying to solve for k, right? Where is k? It's a power inside of an exponent, right? How do I get the power separated from the base? What do you say, Maggie?
Take the log.
Exactly. If we take the natural log of both sides, then I can pull the power away from the base. So this gives me the natural log of a half equals the natural log of e to the 28k, which gives me 1/2 equals 28k times the natural log of e. But what's the natural log of e?
1.
It's just 1. So we get that 1/1/2 is equal to 28k. Sorry, I dropped a natural log there, folks. That made no sense to me. Sorry. I dropped that natural log. Sorry. From this, when I scrolled up, from this line down, I dropped the natural log. Okay. So then we get that k is equal to the natural log of a half divided by 28. Would somebody with a calculator give me a decimal approximation on that k value? So let's maybe call it just negative. Well, no, that might be confusing. So it's approximately negative 0.02475. So maybe we call it that. Approximately. Does it make sense that the k value came out to be negative?
Yeah.
How come?
It's decay.
It's a decay problem, right? So finally, we've got our function. Our function is that a of t equals 50 e to the negative 0.0248 t. And this will model how much of this strontium-90 we have at any point in time. No. But you need to see it. I don't know why we're not required to cover this topic at this point in time. So I'm introducing it. I feel like there's no way you should go through a calculus career without seeing this problem, and it's not in our calc sequence. So, nope. I don't know why it's not. So I put it in. So no, you won't be tested on that. All right, we got 10 minutes left.